In this video, we're going to examine intermolecular forces within a molecule. So we're going to define the three types of intermolecular forces, and then we're going to rank them based on strength. So there's a difference between intermolecular and intramolecular. An intramolecular force is a bond, like a covalent or an ionic bond. An intermolecular force are going to be the forces of attraction between molecules. So the force of attraction between two water molecules would be an intermolecular force. Intermolecular forces are weaker than ionic or covalent bonds. The properties of liquids are going to reflect the strength of your intermolecular forces. For example, when a substance melts or boils, it's the intermolecular forces that are broken, not the covalent bonds. For boiling points, stronger intermolecular forces mean that your boiling point is going to be higher. Same thing for melting points. The stronger the intermolecular forces, the higher the melting point is going to be. So here's another picture. You can see that a covalent bond is the bond between the hydrogen and the chlorine, and intermolecular attraction is the bond between two HCl molecules. They're also called van der Waals forces. They're all electrostatic. In other words, they are attracted to the positive and negative ends, the opposite attract, and they do tend to be less than 15% as strong as your ionic and your covalent bonds. Now, ionics are going to be the strongest bonds, then followed by covalents and your intermolecular forces. Dipole-dipole is one type of intermolecular force. This is where the attractive forces between the negative end of one polar molecule and the positive end of another polar molecule are attracted to each other. Hydrogen bonding is going to occur between a hydrogen that's covalently bonded to either fluorine, oxygen, or nitrogen, and another fluorine, oxygen, or nitrogen with at least one lone pair. Now, hydrogen bonds are 5 to 10 times stronger than other dipole-dipole attractions. But remember that hydrogen bonding occurs between hydrogen and fluorine, oxygen, or nitrogen. It's a special type of dipole-dipole. We do call it the strongest of the weak between hydrogen and FO or N. Now it's greatest between FO or N and hydrogen because they're very polar in nature. Their atoms are so small that the partial charges are caused by differences in electronegativity, and it's highly concentrated. And those lone pairs on fluorine, oxygen, and nitrogen increase the already partially negative charge on the atoms, and then that's going to create a stronger attraction for your slightly positive hydrogen. Hydrogen bonds between between water molecules are shown here. So the hydrogen bonded to the oxygen in H2O, that's a covalent bond. The hydrogen atoms are going to form hydrogen bonds with these lone pairs on the oxygen of another water molecule. And these are fairly strong bonds, which is why water has a relatively high boiling point. It's also responsible for ice floating in water because what happens is it actually spreads out. It gets longer in distance, and so your molecule spreads out. It can actually float in water instead of sink. London dispersion forces, you might hear these called instantaneous dipoles. This is where your electrons repel as they move, and they're going to distort the electron cloud. These occur in nonpolar atoms and molecules, and they're only significant when your molecules are close together. They only happen if they get close. So for example, here we have two helium atoms. There's not much attraction between normal helium atoms until they get closer together. And then the electrons of one helium atom are going to be attracted to the protons of another. And it distorts the shape and it creates a dipole moment, which it means that you're going to have a positively charged area here and a negatively charged area here. Now, they're going to depend on the shape of the molecule. The greater the surface area that's available for contact, the greater your dispersion forces are going to be. The London dispersion forces between spherical molecules is going to be lower than linear molecules because they're not going to have as much room to cause this interaction. So when these guys get close to each other, then they will distort. They'll form those little areas of attraction, and they'll distort one another's shape. So here's the infographic. We saw this in another video, and I'm putting a link to this in the Google folder that will show you the weak dispersion forces, the dipole-dipole interactions, and then your ionic interactions here. And on the infographic you'll be able to read this information a little clearer. I love these pictures here with all the colors. Remember that the green means you're neutral. The areas of red are negative and the areas of blue are positive. Then you can see on an ionic compound where there's a very high boiling point how the molecules are attracted to each other and they keep their own charge. And here's another little chart for you to be able to determine the types of intermolecular forces that are involved in a compound. So what we're going to do is ask ourselves if we have ions. If we do, then we move to this side. Are polar molecules and ions present? Yes or no. If we do not have ions, we look over here and we see if we have polar molecules, yes or no, and we go from there.